Welcome to our channel. Today we're diving into the world of earthquakes to separate fact from fiction. Earthquakes, these profound shudders of our planet, have captivated and terrified humanity for millennia. They're a stark reminder that the ground beneath our feet isn't as solid and dependable as we might like to believe. And like many powerful, somewhat mysterious natural phenomena, a whole host of myths and misconceptions have sprung up around them. Some are kind of harmless, some are a bit silly, but others can actually be dangerous if they lead to complacency or misguided actions. So why does it matter? Why spend time debunking earthquake myths? Well, because understanding the reality of earthquakes, how they work, where they happen, and what they can and cannot do is absolutely fundamental to our safety and our preparedness. Knowledge in this case isn't just power, it's a lifeline. When we replace fear born of misunderstanding with respect born of knowledge, we're better equipped to build resilient communities and to react sensibly when the Earth decides to remind us of its dynamic nature. In this video, we're going to tackle some of the most persistent myths. Head on, we'll look at the science, explore the geology, and hopefully by the end you'll have a much clearer picture of these incredible and at times incredibly destructive events. We're going on a journey from the Earth's core to its crust, from ancient folklore to modern seismology. So buckle up, because we're about to get to the bottom of what really makes the world shake. All right, before we can bust any myths, we need to establish some groundwork, literally. So what exactly an earthquake? At its most basic, an earthquake is a sudden release of energy in the Earth's lithosphere that creates seismic waves. Think of it like snapping a rubber band that you've stretched too far. The Earth's crust is made up of these massive, irregularly shaped slabs of solid rock called tectonic plates, which are constantly, albeit very slowly, moving. They float on the semi-fluid asthenosphere beneath them, kind of like crackers on a thick soup. These plates can grind past each other, collide, or pull apart. Most earthquakes occur along the boundaries of these plates, which we call fault lines. When the stress built up from this grinding and bumping overcomes the friction holding the rocks together, the rock fractures or slips, and that stored energy is released in the form of waves, seismic waves, that travel through the Earth and cause the shaking we experience as an earthquake. It's a truly colossal release of energy, often equivalent to many atomic bombs. Now, the point underground where the rock first breaks or slips and the earthquake energy originates is called the hypercenter or focus. The point on the Earth's surface directly above the hypercenter is called the epicenter, and that's the term you probably hear most often in news reports because it's where the shaking is usually the strongest and where damage is often most severe. Understanding this distinction is pretty key to understanding how earthquake intensity is mapped and reported. These seismic waves aren't all the same either. There are P waves or primary waves, which are compressional, kind of like sound waves. They travel fastest and can move through solids, liquids, and gases. Then there are S waves or secondary waves, which are shear waves that move rock particles up and down, or side to side, perpendicular to the direction the wave is traveling. S waves are slower than P waves and can only travel through solids. It's the arrival of these different waves at different times that seismologists use to locate earthquakes. And then, when P and S waves reach the surface, they can generate surface waves, which travel along the Earth's surface and are often the most destructive. Think of ripples on a pond, but the pond is, the ground. These include love waves, which shake the ground horizontally, and Rayleigh waves, which make the ground roll much like ocean waves. It's these surface waves that cause buildings to sway and collapse, and they're the ones responsible for most of the dramatic earthquake effects we see. So, how do we measure these things? You've probably heard of the Richter scale, developed by Charles F. Richter in 1935. It measures the magnitude of an earthquake based on the amplitude of the largest seismic wave recorded by a seismograph. However, the Richter scale has limitations, especially for very large earthquakes. Today, scientists more commonly use the moment magnitude scale, MMS, which is more accurate for a wider range of earthquake sizes because it measures the total moment release of the earthquake, considering the area of the fault rupture, the amount of slip, and the rigidity of the rocks. It's important to remember that these magnitude scales are logarithmic. This means that each whole number increase in magnitude represents a 10-fold increase in the measured amplitude of the seismic waves and critically about 32 times more energy released. So a magnitude 7 earthquake is vastly more powerful than a magnitude 6, not just a little bit more. This exponential increase in energy is why larger earthquakes are so much more devastating. Why is all this foundational knowledge so crucial? Because if we don't understand the basic mechanics of the ground is shaking, we're more susceptible to misinformation and fear. Knowing that earthquakes are a natural consequence of our planet's geology helps us frame them correctly. It's not some malevolent force, it's physics on a planetary scale. This understanding is the very first tool in our preparedness toolkit, allowing us to approach the topic rationally. This isn't just abstract science, it has very real-world implications for building codes, for emergency response planning, for how we site critical infrastructure like hospitals and power plants. Understanding the types of waves and their effects helps engineers design structures that can better withstand shaking. Knowing about plate tectonics helps us identify regions at higher risk, even if we can't predict the exact timing of the next big one. Ultimately, grasping these fundamentals, tectonic plates, faults, seismic waves, magnitude, is like learning the grammar of the Earth's occasional violent outbursts. It allows us to read the signs, interpret the data, and hopefully build a safer world on this ever-shifting surface. This understanding is our shield against the myths we're about to explore, empowering us to differentiate between geological reality and imaginative fiction. Okay, let's tackle a big one. A myth so dramatic and visually spectacular that it's become a staple of disaster movies and popular anxiety. The idea that California, or at least a significant chunk of it, is going to dramatically break off from the continent and sink into the Pacific Ocean after a massive earthquake. You've seen the images, right? Skyscrapers toppling into the churning sea, a new coastline emerging as the Golden State becomes Atlantis West. It's terrifying, it's cinematic, and thankfully it's almost entirely incorrect. The persistence of this myth is understandable. California is undeniably earthquake country. The San Andreas Fault System, a massive network of fractures in the Earth's crust, runs almost the entire length of the state. It's the boundary between the Pacific Plate and the North American Plate, and these two colossal pieces of Earth's puzzle are constantly trying to move past each other. So the idea of a dramatic rupture isn't entirely out of left field, but the sinking into the ocean part is where geology and Hollywood part ways. The key thing to understand here is the fault the San Andreas is. It's predominantly a transform fault. Now, what does that mean? Imagine two blocks of wood pressed tightly together. If you try to slide one past the other horizontally, that's basically what's happening along a transform fault. The Pacific Plate is moving northwest relative to the North American Plate. It's a horizontal, side-by-side sliding motion. There's no significant vertical movement that would cause a landmass the size of California to just drop off into the sea. Contrast this with, say, a subduction zone. In a subduction zone, one tectonic plate, usually a denser oceanic plate, dives another plate. This process leads to land sinking or coastal subsidence as the overriding plate is dragged down or buckles, but that's not the primary mechanism at play along most of the San Andreas Fault. The motion is overwhelmingly lateral, so while the ground will definitely shake and parts of the coast might experience some localized changes, the state isn't going to detach and capsize. What's happening is that the land on the Pacific Plate, which includes Los Angeles and San Diego, is slowly, inexorably moving northwestward relative to the land on the North American Plate, which includes San Francisco and most of the rest of North America. So, in many millions of years, Los Angeles will indeed be a neighbor to San Francisco, but they'll both still be very much above sea level, just in different relative positions. This movement happens at a rate of a few centimeters per year, roughly the speed your fingernails grow. Now, earthquakes along the San Andreas Fault occur when sections of this fault, which have been stuck and accumulating stress due to this slow, steady plate motion, suddenly rupture and slip. This can cause significant horizontal displacement. For example, during the 1906 San Francisco earthquake, some areas saw the ground shift horizontally by as much as 20 feet. But again, this is a sideways shift, not a plunge into the abyss. It's true that some coastal areas in California are vulnerable to tsunamis, which can be generated by underwater earthquakes, often at subduction zones elsewhere in the Pacific, or by offshore landslides triggered by shaking. And yes, localized land subsidence or uplift can occur after very large earthquakes due to complex crustal adjustments. Coastal cliffs can also collapse due to shaking, but none of this equates to the entire state or a significant portion of it breaking off and sinking. The image is powerful, the fear is real, but the science offers a different, less apocalyptic scenario. The big one, when it eventually happens along the San Andreas or another major California fault, will be a very serious and destructive event, causing widespread shaking, damage to infrastructure, and significant human impact. But it won't involve California taking a dive into the Pacific. The actual geological processes are fascinating enough without the need for Hollywood embellishments. So while it's crucial to be prepared for the very real threat of a major earthquake in California, we can lay this particular myth to rest. The ground will shake, buildings might fall, but the landmass itself isn't going anywhere quite so dramatic. Understanding the mechanics of transform faults helps us focus on the real hazards, ground shaking, liquefaction, landslides, and prepare accordingly rather than worrying about an impossible oceanic plunge. The Earth's plates are engaged in a slow, powerful dance, and California is right on the dance floor. There will be stumbles and violent shoves, but the floor itself isn't going to suddenly give way and swallow one of the dancers whole. The reality of plate tectonics is complex and awe-inspiring, and it provides a much more grounded understanding than the sensationalized myths. Chapter 3. Not just a California thing, earthquake hotspots you didn't expect. When many people, especially in the United States, think of earthquakes, their minds immediately jump to the West Coast, California, Oregon, Washington. And it's true, this region is part of the Pacific Ring of Fire, an incredibly active seismic and volcanic zone that circles the Pacific Ocean. It's where several tectonic plates meet, grind, and subduct, leading to frequent and sometimes powerful earthquakes. So, the reputation is well deserved. However, the myth we need to bust here is that significant damaging earthquakes happen on the West Coast or in similar high-profile seismic zones. The truth is, earthquakes can and do occur in many places around the world, often far from the major plate boundaries that get all the attention. While plate boundary earthquakes are generally more frequent and often larger, intraplate earthquakes, those that occur the interior of a tectonic plate, are a very real phenomenon and can be surprisingly powerful and damaging, especially because these areas are often less prepared. Think about some of the most devastating earthquakes in history. Yes, many are in places like Japan, Chile, Indonesia, all on major plate boundaries. But what about the New Madrid seismic zone in the central United States? In the winter of 1811 to 1812, a series of massive earthquakes, estimated to be well over magnitude 7, struck this region, centered in what is now Missouri. These quakes rang church bells in Boston, cracked sidewalks in Washington, D.C., and reportedly even reversed the flow of the Mississippi River temporarily. This was nowhere near a modern active plate boundary as we typically picture them. Or consider the 1886 Charleston, South Carolina earthquake, estimated at around magnitude 7. It caused widespread destruction and was felt over 2.5 million square miles from Canada to Cuba. Again, South Carolina isn't typically the first place that springs to mind when you think earthquake country. These historical events serve as potent reminders that seismic risk isn't confined to the edges of continents or the Pacific Rim. So, why do these intraplate earthquakes happen? The Earth's crust is a complex mosaic riddled with ancient fault systems, some of which are remnants of past tectonic activity, like old healed wounds that can sometimes re-rupture under new stresses. Even though a plate might seem like a single, solid unit, it's still subject to stress from the push and pull at its boundaries or from processes deep within the mantle. These stresses can slowly accumulate and eventually reactivate these old, weaker zones within the plate. Globally, many regions experience this. Parts of China, Australia, India, and even Western Europe have experienced significant intraplate earthquakes. The key difference is often the recurrence interval. Earthquakes on major plate boundaries might happen every few decades or centuries, while major intraplate earthquakes in a specific area might be separated by many centuries or even millennia. This long gap can lead to a dangerous sense of complacency as the seismic memory of a region fades. This is why understanding the full geological picture is so important. Seismologists study not just active plate margins, but also the subtle signs of stress. and ancient faulting within plates. This helps in developing seismic hazard maps that don't just paint California red and leave the rest blank. Many areas have a low to moderate seismic hazard that still necessitates appropriate building codes and preparedness measures, especially for critical infrastructure. The perception that it can't happen here if you're not on the West Coast can be a dangerous one. While the frequency might be lower, the potential for a damaging earthquake exists in more places than people commonly assume. For instance, the eastern United States has a different geological setting than the West, with older, colder and more rigid crust. This means seismic waves can travel much farther and more efficiently, so an earthquake of a given magnitude in the east can often be felt over a much wider area than a similar-sized quake in the west. Therefore, it's crucial to broaden our awareness. Earthquakes are a global phenomenon, a testament to the Earth's unceasing dynamism. While the West Coast understandably gets a lot of seismic attention, let's not forget the less obvious but still very real risks elsewhere. From the central US to the eastern seaboard, from quiet European countrysides to the vast interiors of continents, the Earth can, and occasionally does, remind us of its power in unexpected places. Dismissing earthquake risk simply because you don't live near the San Andreas Fault is a misunderstanding of how our planet works. The Earth's crust is a complex, interconnected system, and stresses can manifest in surprising locations. Being informed about the specific seismic hazards in your own region, wherever that may be, is a vital step towards personal and community resilience. Chapter 4, Little Tremors, Big Misconceptions. Do small quakes stop the big one? There's a rather comforting idea that circulates sometimes, especially in earthquake-prone areas. The notion that frequent small earthquakes act like little pressure release valves, gently letting off steam from the Earth's crust, and thereby preventing a much larger, more catastrophic earthquake from occurring. It's an appealing thought, isn't it? Like the Earth is sighing instead of screaming. Unfortunately, while the sentiment is nice, the science tells a different story. Small earthquakes generally do not prevent larger ones. To understand why, we need to go back to how stress accumulates along a fault. Tectonic plates are pushing against each other, and the fault line is where they're stuck due to friction. This is like pressing two rough bricks together and trying to slide them. Stress builds up over years, decades, even centuries. A small earthquake, say a magnitude 3 or 4, releases a tiny, tiny fraction of the total accumulated stress that a major fault segment is capable of storing. Think about the energy release we talked about earlier with the logarithmic nature of the magnitude scale. A magnitude 7 earthquake releases roughly 32 times more energy than a magnitude 6, and nearly 1,000 times more energy than a magnitude 5. To release the same amount of energy as a single magnitude 7 earthquake, you would need about 1,000 magnitude 5 earthquakes, or tens of thousands of magnitude 4 earthquakes. Those little tremors just aren't doing enough heavy lifting to significantly reduce the overall stress on a large fault. It's like trying to prevent a massive dam from bursting by poking a few tiny holes in it. The amount of water, or in our case stress, is so immense that these small releases are almost negligible in the grand scheme of things. The fault is still locked, the plates are still pushing, and the vast majority of the strain energy remains stored in the rocks, waiting for a much larger rupture. Now, it's true that sometimes a swarm of small earthquakes, known as foreshocks, can precede a larger earthquake. In these cases, the small quakes aren't preventing the big one. They might actually be indicators that the fault system is becoming unstable and approaching a critical stress point. However, not all earthquake swarms are followed by large quakes, and many large quakes occur with no discernible foreshocks at all, making them very difficult to use for reliable prediction. Conversely, a long-period small earthquakes in a historically active area, known as a seismic gap, can actually be more concerning to seismologists. This might indicate that a particular segment of a fault is completely locked and accumulating a very large amount of stress, making it a prime candidate for a future major earthquake. So, a lack of small tremors isn't necessarily a good sign, and their presence isn't necessarily a pressure release. The science of earthquake prediction is incredibly complex. Despite decades of research, we still cannot reliably predict the exact time, location, and magnitude of future earthquakes with the kind of precision that would allow for timely evacuations. We can identify high-risk areas and estimate probabilities over long timescales. For example, a 30% chance of a major earthquake in a certain region in the next 30 years. But that's very different from saying a big one is coming next Tuesday. So relying on the idea that small earthquakes are taking the edge off and making a big one less likely is a dangerous misconception. It can lead to a false sense of security and a reduction in preparedness efforts. The reality is that major earthquakes occur when the accumulated stress on a large segment of a fault finally overcomes the frictional strength holding it together. And this happens largely independently of the minor creaks and groans the fault might make along the way. These small quakes are certainly interesting, and they provide valuable data for seismologists studying fault behavior. They map out active fault traces and help us understand the ongoing tectonic processes. But they are not safety valves in any meaningful sense when it comes to preventing the immense energy release of a major earthquake. The forces involved in plate tectonics are simply too vast. Therefore, when you feel a small tremor or hear about one on the news, it's a good reminder that you live in a geologically active area. It should prompt you to check your preparedness kit and review your safety plan rather than thinking, oh good, that's one less big one to worry about. Understanding this helps us maintain a realistic perspective on earthquake hazards and the importance of long-term preparedness. The Earth doesn't really do gentle releases when it comes to the enormous stresses built up along major fault lines. When those faults decide to move in a big way, they do so with incredible power, and the preceding minor shakes are more like the cracking of an overloaded beam than a controlled release of pressure. It's a sobering thought, but one that underscores the need for robust science-based preparedness. Chapter 5, Fido's Foresight or Fanciful Folklore. Animal Earthquake Predictions. This is a classic, one that has been around for centuries, probably as long as humans have lived alongside animals in earthquake-prone regions. The belief that animals can predict earthquakes. We hear stories, dogs barking incessantly, cats hiding or acting erratically, birds taking flight en masse, snakes emerging from hibernation in winter, even fish behaving strangely, all supposedly just before the ground starts to shake. It's a compelling idea that our animal companions or wild creatures possess a sixth sense, an early warning system that we humans lack. The appeal is obvious. If animals could reliably predict earthquakes, it would be an incredible boon for humanity, potentially saving countless lives. And there's a wealth of anecdotal evidence. Historical accounts dating back to ancient Greece describe unusual animal behavior prior to destructive quakes. Many people who have experienced earthquakes firsthand will swear that their pets were acting strangely, minutes, hours, or even days before the event. So, what does science have to say about this? Well, it's complicated, and the scientific community is generally skeptical about animals possessing a true predictive ability in a way that could be systematically used for warnings. That's not to say animals aren't sensitive to their environment. They absolutely are, often far more so than humans in certain respects. Many animals have keener senses of hearing, smell, or can detect vibrations that are imperceptible to us. One leading hypothesis is that some animals might be sensitive to the very subtle P waves, the primary seismic waves that travel faster than the more destructive S waves and surface waves. P waves are often too weak for humans to feel, but an animal with acute senses might detect this initial faint shaking seconds or even tens of seconds before the strong shaking arrives. This isn't prediction in the sense of knowing hours or days in advance, but rather a very rapid reaction to the earthquake already beginning. Other theories suggest animals might be reacting to changes in the Earth's electromagnetic field or to the release of underground gases like radon, which can sometimes increase before an earthquake as rocks are stressed and microfractures open. Some animals are also highly sensitive to changes in groundwater levels or chemistry. It's plausible that some creatures pick up on these subtle environmental precursors that we are oblivious to. However, the big challenge for science is consistency and reliability. For animal behavior to be a useful predictor, it would need to be specific. The behavior only happens before earthquakes, not for other reasons. Reliable, it happens before most or all earthquakes, and observable in a way that can be clearly distinguished from normal animal behavior. So far, no single animal behavior or species has met these criteria in rigorous scientific studies. The problem is that animals act strangely for all sorts of reasons: hunger, fear of a predator, mating rituals, illness, or even just a change in the weather. It's very difficult to definitively link a specific unusual behavior to an impending earthquake, especially when earthquakes are relatively rare events. There's also the issue of confirmation bias. We tend to remember the times when the dog barked like crazy and then an earthquake happened, but we forget all the times the dog barked like crazy and nothing happened. Scientists have conducted studies such as placing cameras in areas with high seismic activity to monitor animal behavior, or analyzing large data sets of reported unusual animal behavior. The results have largely been inconclusive or have failed to find a strong, replicable correlation that would be useful for prediction. The US Geological Survey, for instance, states that despite numerous attempts, no one has ever successfully predicted a major earthquake using animal behavior. This doesn't mean all the anecdotal stories are false. It's very likely that animals sometimes react to subtle environmental changes that precede or accompany the very earliest stages of an earthquake. But translating these individual, often ambiguous reactions into a reliable scientific forecasting tool is an enormous leap that we haven't been able to make. The signals are likely too noisy and too varied, so while it's fascinating to observe our animal friends and the natural world around us, and while their heightened senses are truly remarkable, relying on Fido or Fluffy to give you a heads up about the next big one isn't a scientifically sound preparedness strategy. Our best bet still lies in understanding the geology, building safer structures, and having robust human-designed early warning systems where possible, which are based on detecting the earthquake and transmitting alerts rapidly. The idea of animals as natural seismometers is enchanting, a testament to our deep connection with the living world. But for now, it remains largely in the realm of folklore and intriguing but unproven possibility, rather than established scientific fact for reliable prediction. We should continue to study it, of course, because science is about exploring the unknown, but we shouldn't bank our safety on it. Chapter 6. Beyond the myths, staying grounded in reality. So there you have it. We've journeyed through the Earth's crust, explored the mechanics of plate tectonics, and hopefully dispelled some common but persistent myths about earthquakes. From California taking an unlikely plunge into the ocean, to the idea that small quakes prevent big ones, or that our furry friends hold the secret to seismic prediction, it's clear that when it comes to these powerful natural events, facts can often be just as fascinating and certainly more useful than fiction. Understanding that earthquakes are a global phenomenon, not just a West Coast specialty, and knowing that their occurrence is governed by immense geological forces that don't really let off steam with minor tremors, helps us approach the topic with the seriousness and respect it deserves. It allows us to focus our energy on what truly works: scientific research, robust building codes, comprehensive preparedness plans, and fostering a culture of awareness and resilience in our communities. Earthquakes are a profound reminder of the dynamic planet we inhabit. They will continue to happen, but by arming ourselves with knowledge and cutting through the fog of misinformation, we can reduce their impact on our lives and our societies. It's about replacing fear with understanding and helplessness with proactive preparation. That's the real power we have when facing the shudders of the earth. Thanks for watching. If you found this video helpful, don't forget to like, share, and subscribe for more informative content. Stay safe and stay informed.